To the Minnesota Stormwater Seminar Series, or MS3 as we are currently calling it. The Minnesota Stormwater Seminar Series is co-sponsored by the Water Resources Center and the St. Anthony Falls Laboratory, both at the University of Minnesota. My name is Jon Gulliver, and I will introduce our speaker. We are very excited to have Jon Hathaway as a presenter. Jon has worked at Biohabitats, an environmental consulting firm, and also at North Carolina State University as an extension associate. He has his BS, MS, and PhD degrees from North Carolina State University, where he finished his PhD under Bill Hunt. He did this in under 3 years, which I think must be some sort of record. I don't know. He is currently an associate professor of civil and environmental engineering at the University of Tennessee, winning multiple research and teaching awards. Jon has a broad range of research activities in stormwater infrastructure. Today, he's going to talk about trees and bioretention systems. Please join me in welcoming Dr. Jon Hathaway.
All right. Thank you, I appreciate it. It's great to be here today. We were leaving breakfast this morning and I had to ask the question, I was like, is everyone in Minnesota this nice? It's like very nice people. And obviously you're probably aware, but it's an honor to be here. This is one of the most well-respected stormwater groups in the country. And so it's always an honor to come and speak and kind of exchange ideas with other people. So I'm going to talk a little bit about some work that we've been doing with trees. Both the focus of this will really be like, what are trees doing inside of these bioretention systems, inside of green infrastructure systems? And I owe a great deal of this work to Dr. Andrew Turpak, who did his PhD with me and now is a postdoc at Ohio State University. You know, he's published, I think, 4 papers out of this PhD work. Just a really great researcher. And so, as most advisors do, you know, I take his information and then I present it. So, and the next is I'm going to show a few slides on some things that we've done with tree interception. And that's, we're working with one of my current students, Matthew Howard, on that. So most of the work that we're going to talk about was funded by the U.S. Forest Service as part of their NUCVAC program. And I've worked a lot with Eric Keeler. He's in Athens, Georgia, as part of the that Forest Service one of their offices out there. We also collaborate a lot, so I will say I am not a forestry professional, and so there's a lot about trees and tree physiology and tree function that, you know, really as engineers, it's important to get perspectives from lots of other people, and the best kind of projects are when we can collaborate and learn from each other. And so that's what we've done with Dr. Franklin. She is a tree physiology specialist at UT. So I was excited to come here, and Andy emailed me and said, would you come to Minnesota and speak? And I was like, absolutely, that's awesome. He was like, we've got an opening in January. And I was like, okay. So, you know, the first question is like, can a Southerner survive in Minnesota in the wintertime? And then they said, you want to go ice fishing? And I was like, all in. Absolutely. So this is us ice fishing yesterday. We had a bunch of fun. I obviously never done this before. And so, you know, opening up a hole in a floor and putting a fishing lure down there, it's surprisingly very fun. And good times, much warmer temperatures inside the building than outside. I've been really like enamored with this, this figure for a long time. This is a researcher at University of Melbourne, Tim Fletcher, and they put together a team of people and they started looking at the evolution of stormwater management and mostly looking at different terminology and different locations. But this schematic in particular is interesting and kind of tells us where we've gone over the past 50 to 60 years in terms of stormwater management, where, you know, 50 or 60 years ago, we were talking a lot about flood mitigation, peak flow reduction, and over time, we've kind of shifted and had higher expectations of our stormwater infrastructure, where now we're not just looking at flood mitigation, we're looking at volume control, we're looking at aesthetics, we're looking at social elements of green infrastructure. And so as those things have developed, we've turned a lot to these bioretention areas. And so this is just a schematic that shows us what's going on. In terms of hydrology, right, this fits the bill for a lot of things that we're trying to do. We get exfiltration, we get treatment through the sandy media, we get some evapotranspiration. But what we find is that a huge element of this, if we actually are going to look at that figure and fit the bill, a lot of things have to come from the vegetation in this this cross section, right? And so trees have a lot of benefits in the urban environment, and they've been studied in a lot of different conditions for what they do. In terms of hydrology, it's pretty well established that you get a lot of infiltration from trees. We get through fall benefits. We get a lot of things like that. But they're doing a whole lot more in the urban context. So at the individual level of a tree, we're also getting things like uptake of CO2. We're getting reflectance of heat. We're actually getting some air quality improvements. If we look at kind of the bigger scale, we start looking at heat island reduction. We start looking at energy savings when we are shading buildings in the summertime. And so when we look at this holistic vision of a city, these trees and vegetation play a huge role in kind of the overall livability and sustainability of a city. Now, what's interesting in terms of bioretention is that a lot of times, I'm an engineer, so I can talk about engineers, but we're very good at figuring out, taking a design manual and following that design manual, right? And so when we look at how plant selection has gone historically, people have either anecdotally looked at, what vegetation has survived, or maybe we've looked at guidance documents from urban forestry. We haven't really done a lot to match basically what is the physiology of a given plant and how does it match this specific environment. So what we've done in particular for trees is try to determine how healthy are trees inside of bioretention areas. Do they actually like this environment? What are they doing in there? And how can we better match the tree physiology and what a tree wants with what we're providing it inside of these systems? So that was basically our big research goal at the beginning of this study, was to kind of quantify and to investigate some of these things. So the first thing that we did is we went to kind of a survey. We wanted to go through and look at over about 100 trees in various locations in the Southeast, in Nashville and Chattanooga, and over in the Triangle, Raleigh and Durham. And this is kind of our first step, was to kind of go out, survey trees that are in bioretention areas and say, do they actually like this environment from what we've been seeing? And the way that we do that are these crown condition indicators. This is just methodology taken from forestry, where you get a couple of observers and they're doing these partially qualitative, partially quantitative inspections of trees. So they're looking at things like crown dieback that you see here, crown density. So what portion of the tree, if you were to visualize what the tree should be if it was filled out, how much of that space is actually filled? Transparency. So how much can you see through that canopy? And so we can pull these things together in what we call crown composite indicators. And the idea is that if we have a higher crown composite indicator, we have a more healthy tree. And so we compile these into crown indicators. And so we took this data for all the trees that we collected, and then we pulled from some surveys done by various cities and municipalities and entities in the area. So a lot of people have used iTree and collected data about trees. We took that data from them and basically came up with these crown composite indicators from just urban trees, right? Not necessarily in a bioretention area. And the results were a bit surprising to us. So these are the most frequent species that we saw down here on the bottom: red maple, river birch, pin oaks, bald cypress. And by and large, what we were finding is that trees inside of bioretention areas, which are the darker areas here, were less healthy on average than ones outside of bioretention areas, right? The only exception that we saw was over here with our bald cypress. So we actually got better indicators for those systems. And when we start looking at why that's the case, it really comes back to tree preferences. And we went into literature and you start looking at what different environments do trees like. You see that various species, just because they can tolerate a given environment, doesn't mean they necessarily thrive in that environment. There's what's happened in tree specifications in bioretention is we've tended to take urban trees or trees that have been spec'd out in urban settings and just kind of assume that those are going to work inside of a bioretention area, which doesn't necessarily seem to be the case. So when we look at some of these species, for instance, you'll see river birch actually prefers clay soils with high soil moisture. Pin oaks might like heavy texture, poorly drained soils. And then the bald cypress down here, we see it a lot in kind of riparian. You think of it as more of like a water-loving species, but they can actually grow pretty well in sandy loam soils, provided they don't have competition from other trees. And so there's a lot I think we can learn about what trees are going to survive these environments based on studies that we've seen. At the same time, we collected a bunch of data on like the type of soil that we had out there, the soil chemistry, various like where was it planted inside of the system. And we use what we call random forest. It's just a machine learning technique. It's able to take information, look for associations, and pick out like what are the most outstanding or most impactful variables in a system. So those high importance parameters were first, we can categorize those into media composition, media chemistry, and then tree selection and planting. So what are we actually putting in the soil? Had a lot to do with tree health. What was in that tree? So do we have a lot of copper, potassium, et cetera? And then planting location. And as we talked about this a little bit yesterday, a lot of times in our bioretention media specifications, we look at a few small factors. So we specify these hydrologic factors, and then we may talk about phosphorus or a few elements, but we don't really talk about micronutrients, anything that might really be associated with plant growth. And so there's probably a lot of work to be done in terms of like being a little bit more specific in our media specifications about what we want our soil chemistry to be like. So the outcomes of this were really that we've got to look more at picking the right tree for the right circumstance. And that doesn't just mean a tree that works well in an urban setting. It's a tree that's kind of specifically good for this bioretention environment. And I think there's a fair amount of work to be done to work with the forestry community to figure out what really fits the bill. So we moved them from there to try to understand more about the performance of trees inside of bioretention areas. And does that performance vary based on species? We did this huge kind of study looking at these different columns and essentially looking at different tree species and trying to measure what they're doing inside of these systems. This is one of those classic, like, write a proposal, don't, maybe like wrote a check that you didn't understand exactly what was going on. I was like, we need to do giant columns because trees need a lot of root volume, right? Like, you got to have a big column. What I didn't think about is that each one of these is like 600 pounds. So once we built them, we were like, they got to basically stay there. You can't do anything with them. So we made these columns and we essentially put them on top of these scales down here. And so the scales allow us, it basically acts like a lysimeter. We can look at change in weight over time, and you just relate that to change in water. And so we can get at like what's the evaporation, what's the transpiration rates in these systems. So kind of a classic mix of hardwood mulch and then the bioretention media, and then at the bottom we have this scale. So we use this synthetic stormwater. It allows us to do a little bit more of like a regimented experiment than using our actual stormwater. We based on 30 years of data from Knoxville about a 0.2-inch storm and kind of made that relative to the opening of the column. Then we basically would apply water every, I think it was 3 times every 2 weeks was like our regimen. And what we get from our scale data, I'm going to talk specifically about the hydrology today, is we get this. So this is the example of weight and how the weight changes over the course of a sampling event. So you pour water in, obviously the weight goes up, and then you get this free drainage that occurs out of the bottom, and then you kind of start getting a little bit more of a moderated flow. So what was interesting to us looking at the data, we were like, what is going on with these steps down here? And Dr. Franklin, who I work with, was like, well, that's probably like evapotranspiration. We were like, that's awesome. So what you start seeing is that when we get these lines out here, these were all nighttime values, right? And so during the night, we'd essentially, tree would shut down, we'd get basically flat weights. Next day would come in, we'd get a drop based on evapotranspiration, flat rates, etc. So we used a bit of a smoothing algorithm on this to iron out our data. And what we were really looking for is, at what point do we get this line straight? Because if the line is straight, it means that free drainage is done. We're not getting any more drainage out of the bottom of the system. All we're getting is this evapotranspiration. And so we were able to use this to get an idea of how much water loss we're getting from our columns and from the different tree systems. So in this case, we could take a line once we saw these plateaus and get an idea over the days of how much water we'd lost. So we can compare these. We had some that were non-vegetated systems and some that were vegetated. And so when we look at this, you can see from the loblolly pine and the pin oak, we get about a 20%, an additional 20% of losses of water out of a system like that. Down with the red maple, we got a huge difference in the amount of water we lost from those bins relative to non-vegetated. The red maple took off in these things, was really happy, growing like close to the top of the greenhouse. And so what we see is that this bigger tree down here tended to work much better. And so we think it's pretty positive information, pretty positive results that in a system like this, as a tree matures, starts taking over more and more space, it's actually going to contribute pretty highly to the amount of evapotranspiration that we see inside of a system. So we think there's pretty large benefits of trees in terms of hydrology. There's a bunch of studies that have, or a few studies that have started to look at this. Some studies that looked at plant contributions to hydrology are a little bit more like a qualitative. Some of them are quantitative. But if you look at some of these numbers like Lee et al., 20% of the water loss is due to ET, 4 to 5%. This one says 3%. So I think we're starting to kind of dial into to the additional benefits of trees in terms of ET. And I think 20% is probably like a minimum amount of what we're going to see. So how do we translate this to the practice scale? So in our studies, we were also able to take some of these things and pull them into a site scale project. So we use these suspended pavement systems. I'm sure most people are familiar with these. And the idea is that trees in urban environments are really kind of hampered by compacted soils. And so if we can provide some unconsolidated soils close to the tree, it gives the roots a lot more access to air. It gives the roots place to grow. And so in systems like this, these are made so that the load is basically carried by that plastic structure and the soils can remain uncompacted, right? And there's a few different companies that make these. We use Silvacell in our study. So we have a little site on campus, a little drainage area. We were able to build 2 of these practices on campus. So this is a cool study for Andrew. He got to actually like design and build some stuff also in his PhD. And so what we did is we had water coming in from a curb cut. We put that into this pipe over here, a big distribution pipe. The water comes down, and then we have these drains on the bottom. So what we wanted to test is what's the difference between a system that is just sealed off, no drainage, versus one that has drainage. And so you'll see northern site, the northern site basically had no drainage. The southern site, we had an open bottom on that. We wanted to look at the difference, like, do you get difference in volume reduction between those two systems? All right, and so this is kind of our general lineup here. We had bald cypress in there. We had monitoring equipment set up to look at these different values, and then we had this sap flow sensor that we'll talk about here in a minute. All right, site design. One of the things I'll point out is we had very, very, very low loading ratios, and that was partially a product of the design. We'll talk about that in a minute, but you know, there's a lot of different design standards from you have to store all the water in the top of a bioretention area to some design regulations that give you credit for void space in the soils. And what we found is with these systems, you only get about 3 inches of ponding or about at the top of the system. So if you design them from that surface level ponding, like I want to keep all the water in the top of the system, you end up with a huge system relative to what your drainage area is. And we'll show how that shows up in the results and talk about that in just a minute. All right, so here's our construction. We had some guys on campus help us out with this. It's a pretty cool process. You put down these plastic liners, you fill it up with soil, you kind of stamp it around in there to get the soil compacted. And then we came back in and had our monitoring at the inlet. We were capturing any overflow that happened from the system and also anything from our under drains. So from a hydrology standpoint, this northern side that was capped worked very, very well. We had just a little bit of overflow, lots of exfiltration and ET, and even the southern site worked very well in terms of, we had about 10% outflow, but still really good performance for a system like this. Again, this is partially due to, you know, the size of our project, but over the long haul, if you know, it's pretty much equivalent to what you would think of with a standard bioretention area. We looked at these discharge thresholds. This just tells us like what size storm can something capture without seeing overflow. And so for the northern site, that was about 9 millimeters, so about 1/3 of an inch. And then, but if you look at, even when we did see outflow, like really, really small volumes. So pretty good performance from that. At the south site, we saw a little bit bigger in terms of about 1/2 an inch before we saw outflow. And so in general, both systems performed really, really well. So we think these suspended pavement systems can be just as effective as any other bioretention area. They haven't been studied too much in terms of their performance as a stormwater practice, but they seem to be fairly equivalent. The other thing is that I really think we have to look at how we size them. So, you know, taking credit for void spaces is going to tend to allow a smaller practice size per watershed area than just looking at, you know, this bowl storage or how much water can fit in the storage space above the media. So I think there's really kind of this sweet spot for systems like this. So you're trying to balance the fact that every tree needs a certain volume of soil in order to, you know, have enough space for its roots, but then you're trying to fit that amount or what that surface area is to a watershed size, right? It's a bit of an optimization problem of, you know, you could have a system that's there's like I guess a minimum size that you're ever going to want for one of these systems just to make it have enough root volume, right? So you kind of have to figure out the watershed that's going to match that necessary root volume. We also need to look more at pollutant removal. We had a pretty low influent concentrations and small sample sizes just based on the lack of overflow from our system. Okay, so the last thing from this study that we wanted to look at was, what are the trees actually doing inside of these systems? Do the differences in systems make a difference to the tree? And so we used these sap flow sensors And how these work is it's a series of 3 probes. So the middle probe is basically a heating element. So it heats up the sap. And then the elements on the top and bottom are basically sensing that heat transfer, right? And so what you can get is basically the rate of sap flow either up and or down inside of the tree trunk. It's not an exact measurement of transpiration, but it's basically a proxy. So you can look at that rate as how much transpiration is going on inside of the system. All right, so this is basically what we look. We got these from this group in Australia that we were that we found them at. I told my student this was this was a Christmas present to myself. This is one of those tools where I was like, this looks cool. We should try this. So over the course of the study, if we look at those northern and southern cells, you can see that by and large, that northern cell with the capped outlet had higher water levels, and it tended to have more transpiration going. So let's take a look at what those trends look like. So this is the northern site over here. This is my southern site. And then these are rainfall conditions down here, okay? So this is an example of where engineers need help. When I was first working with our forestry professor, I was like, this is gonna be awesome. We're gonna see rain like pour into the system, and then the tree's just gonna like take off with transpiration. And this was like my idealized sign. And she was like, well, you know, some trees completely shut down when they're inundated with water. It's like, I did not know that. So, so we basically see that trend to some degree, that when soil moisture conditions get to an excessive point, if depending on the species, the tree will react to that. And so you can see we have a big kind of load of water that comes through here, and you see these pretty low transpiration rates relative to the surrounding days. So we would see events where the tree would be like trending up, it would rain, it would basically just stop transpiring for a while. Soil moisture would go back to where it wants it, and then it would pick back up again. So pretty like fascinating for me, like to see some of these trends that that we did. The other thing that was interesting is we did some regression models to see, like, do these two trees act differently in the systems that they do. One of the ways we can tell that is these atmospheric moisture conditions, and we look at vapor pressure deficit. So what that tells us is what's the vapor pressure that the atmospheric conditions can support versus what's the vapor pressure right now, right? And that difference tells you what's the capacity for the atmosphere to take more moisture, okay? So it tells us like how much transpiration, evaporation could we possibly get, or could the atmosphere possibly hold relative to the moisture that it has right now. And what we found is we got pretty good relationships, but that the northern cell was much more reactive to that deficit than the southern cell, right? The cell that had more water available in the northern cell was getting, basically the tree was giving more transpiration off, right? And so trees have this ability to regulate their transpiration rates based on conditions. If they know that there's no water limiting conditions, they can look at this vapor pressure deficit and just transpiration. If they know there's drier conditions, or they're in a setting where drier conditions are going to be prevalent, they tend to moderate themselves more. And so they tend to, this vapor pressure deficit is not as dominant because they're also trying to regulate their amount of transpiration based on water conditions. So pretty fascinating of all these things that are going on inside of these vegetated species. And as Dr. Gulliver was talking about yesterday, he was like, so it seems like if you have a wetter environment, you get more transpiration, and that seems to be the case from the data that we have. So we get these significant differences depending on the environment that you put that species in. So other things that we've been working on, we've been looking at a few different types of research that's kind of spawned off of this. And one of those things, I've talked to a few people here about these infiltration trenches that are going in with trees. And this is kind of analogous to some systems that we're working on with the Forest Service. So this was an idea that Eric Keeler had. And it was basically like, you know, if we just take gravel supports 40% storage volume, And there's actually places like Athens, this is the county that Athens, Georgia is in, where they grow their trees in gravel. And then, you know, when it's time to transplant them, they will move them to a new location, right? And the idea was that we can get tree growth, or trees can survive inside of these gravel beds. And so we've been working with him a little bit on these different systems to look at what can we do with gravel tree pits, as we're calling them. And so the idea of these is that we can take right around, we would plant, we have like a 3 or 4 foot cube that we plant. We put the tree inside of that cube, and then we essentially drill holes in that cube, in that wood box, to allow the roots to get out of there. And then we surround the entire site with this wash 57 stone, right? So the tree essentially gets minerals and nutrients from that surrounding mineral soil, and then the roots move out into the surrounding gravel to pick up water. And so we have these wells that we put into our system, and you can see the tree roots basically moving out of the box and going into the gravel system. So this tree has grown like crazy over the past like 4 years. It really seems to like that environment. We're doing another study that we should be doing in the next year or so, where we're looking at a few different tree species and trying to put a little bit better. This was like a really like, let's just see if this will work. And we did a little bit of monitoring, but we're looking at doing another study where we can really try to quantify, you know, what are the volume reductions that we get from putting in these gravel tree pits. But in terms of cost, like just they're a lot cheaper. When you get rid of the bioretention media, you can save a lot of money on the device. The other things that we've been looking at are canopy interception. So this was another thing brought to us by the Forest Service. And the idea is that a lot of interception studies are in forested environments where you have a big canopy and you've got different levels of trees in there, different levels of you've got your understory, et cetera. And so looking at what an individual tree in an open grown environment does is not very common in literature. And so we've done this study working with the city, where we have 3 different tree species, and we're monitoring 3 different trees. And then we have these setups out there where they look crazy in the field, but it's like these big half pieces of PVC. We route that water down to a rain gauge. And so during events, we can look at how water is basically moving out of the canopy. Now, one of these we put right next to a playground at a park. And the playground, kind of on the bottom, is all these little gravel, right? And so we always say, like, if you're a little kid and you see this thing and you got a bunch of gravel, you know what you're gonna do. So we had a few problems with these being filled up with gravel and stuff like that over the course of the study. We tried to put fencing around it. I mean, it was pretty funny. It's like us versus the kids trying to figure out how to get our data. But we're getting some really interesting data, and we've collected, I think about close to, I think it's close to 100 storms, maybe 80 or 100 at each of these trees. And this is the kind of stuff that we're getting. This is rainfall at like an open gauge that we have. This is throughfall. And so the tree affects that rainfall in a few different ways. It obviously takes up water. So the difference between these lines in a vertical sense is the amount of throughfall capture that you have. And then it also changes your intensity of your rainfall. So if you look at the slope of that line versus the slope of this line, for instance. So we see like changes in basically rainfall intensity and changes in the amount of rainfall that moves through that canopy. So we have a student working on all this data right now, and he's getting pretty close to having it all compiled. But we think there's some interesting lessons here in terms of what does a tree really contribute in terms of rainfall retention. Our numbers are kind of, I was talking with someone earlier in that, you know, on a yearly basis or throughout the study, we were in that 30 to 40% of rainfall being captured in this system. And some of the amounts of interception are pretty high. So they can add a pretty substantial storage zone into the system. We also look at seasonality, so it depends on if you have a deciduous or an evergreen tree. Over here, we've got the white pine, and it's basically got pretty consistent interception over the course of the year. If you look at willow oak or red maple, you know, they have differences depending on the time of year. We also see differences based on rainfall intensity, rainfall duration, and so we're looking at ways to kind of what are the controlling factors for these species. There's been some interesting work that's come out of, I think it was Belgium recently, where they're trying to get at modeling some of these through fall dynamics. So that was kind of a quick run through some of our forestry work that we've been doing. Like I said, Andrew has put out a number of papers, and so if you're interested in looking at any of those, you can feel free to email me. I'm happy to share things with you. And last night, apparently, I spelled my last name wrong. So I assure you, we didn't get out and party, but apparently that happened anyway. So yeah, so I'm Jon Hathaway. So I'll just open it up to any questions you all have.
Okay, thank you, John. So questions for John?
Thanks for the presentation. In Minnesota, we get snow. Any thoughts about how we would deal with snow interception, and how do we just subtract that off in our annual calculations if we're trying to estimate interception? Any thoughts about that?
That is an interesting one. I always tell my students, I'm like, we don't talk about snow melt in class because it's just not an issue here. But yeah, I think the snow adds obviously an element of, there's two things. And one thing I talked about with people here is just like, how do you keep you know, dirt, salt, et cetera, from getting into your system? So we've tried to experiment a little bit on this next thing with the gravel tree pits. We're going to look at doing some pre-treatment before we allow water into the system. So I think that's going to be important. And then from an interception standpoint, I think it kind of depends on, you know, a lot of times for us, rainfall is coming down. It's directly impacting, you know, the stream system. And so that like, you know, the storage that happens at that moment is really important. With snow melt, I think it would be, or with snow, I think it would be different because that melt is almost like a delayed melting, right? So I think it would kind of depend on how frequently that storage gets refilled. So if the snow gets melted off and provides more space for the next event, I think you'd have to look at how often that storage space is available.
Okay, we have a question from online.
Why was interception of willows higher in winter than in fall in your data set?
It's a matter of the type of storm that happens. And in some cases, if you had low intensity, or in the summer or spring, if you had higher intensity events, it really plays with the interception numbers. So it's not just a product of the tree itself, it's also the rainfall characteristics. So I think when we evaluate that data, we're going to pull out some of those, like, what about the rainfall and the rainfall patterns is affecting that also.
So the first two of my questions. First one would be, we looked, when we try to incorporate the quantified benefits from trees in stormwater management several years ago here for our Minnesota Stormwater Manual, we looked at canopy interception, and it was mostly based on literature values at the time, and this is what, maybe 6 years ago or something? 10, time flies. Our numbers were much lower. I mean, you're talking 30%. We were like 3 to 5, weren't we? Something like that. So the first question is, what do you think the explanation for that is? The other question would be, one of the things I've been curious about is designing a tree system, and instead of depending on the variability of the weather completely for the water regime to the trees, you set up a storage system, relatively small, very small pumps, and then drive the water into the tree system in a designed sort of way. Have you considered looking at a system like that and perhaps comparing it to the natural variability to see if it's optimal or, strong advantages?
Mhm. Yeah. The transpiration numbers, or the interception numbers, we were surprised at how high they were. But when we looked back in some of the recent literature, we get fairly similar numbers to what people have shown in the past few years. There is a difference between, like, individually grown trees tend to have a better developed canopy, and so you do get some effect of that. It's also interesting because a lot of those studies have looked at, like, year-round averages of losses, and we're also interested in getting at, like, numbers, like what is the average amount of interception. So I think based on the studies that have come out recently, it seems to be fairly in line with what we've seen. Like you're saying, it's only been in the past, I would say, 4 years or so, this trying to quantify this interception has taken off, and there's been a lot of people working on trying to do this, both nationally and internationally. So I think if you were to do that search now, you would get probably more information. The second one, it's a very interesting idea, and I think that is what I've heard people start to talk about. There's a group at Berkeley right now it's not quite that problem that you're talking about, but they're looking at if you were to redesign a stormwater system and think more about like unit processes and like an engineering approach, how would you redesign that? And the idea of the sporadic nature of stormwater is very difficult for treatment systems. And so I've seen people start to talk about, like, storage tanks, pump it out at some, like, known rate into a treatment facility. So I think we're starting to see some people look at those things now.
Okay, we have a question in the back.
For your gravel tree pits, have you found any species more suited for that, or is it still too early in the research?
Yeah, so we were working with Chattanooga. We were like, we know bald cypress works. And they were like, we don't want bald cypress all over the city. I was like, okay. So that's part of that next study, is we're using some different species, and we're trying to look at, are there other options that perform well in those too? So right now, I would say we don't know, but we're trying to work on that information over the next, like, year or two.
We have another question from online.
Could you give some more description about the tree in a box example that you showed? There's questions about the dimensions of the box, the size of the area contributing, the river stone, soil subgrade.
The river stone's just purely aesthetic. That was an engineer's attempt at making it look better. Yeah, so we have some design specs for that. And if people want to email me, I am happy to talk about those things. But in general, we're sizing it based on, like, a typical stormwater treatment practice. So we would size it basically equivalent to what we would do with a bioretention area in terms of, like, the amount of storage and the size of the unit. That box is about a 4-foot cube, pretty much. And so I think there's a little bit of work to do to figure out what material you should make that out of. Right now, we just use wood and basically drilled holes in the side of it to let the roots go out. Based on the wells that we see, like, they are leaving the system. And so, I think I think the design itself probably, there's definitely some work to be done to refine it, but it does seem to work pretty well. The soils on this site, Knoxville's got mostly like sea soils. So they're like, they do infiltrate. They're not super infiltrating. Was there any other questions? I can't remember.
What was the cross section like in the tree in a box?
So it was about I think it was 4 feet of rock. And I think the whole thing was about maybe like a 10 to 12 foot kind of square. And it's got that 4x4 square in the middle. But I don't think there's a hard and fast rule to that. I think it's just a matter of getting the volume that you need. The tree will kind of adapt to that environment. So the ones that we're going to be experimenting with, we're going to put like a little bit of a storage zone in the bottom of them. And we think that'll help kind of promote this transpiration that we're trying to get out of them.
You mentioned when designing the system that the soil volume next to the tree there, you considered, the nutrients that the tree would need to take up because they would be void in the gravel area of this. Was there calculations made to a certain maturity level of the tree at some point in time, 30, 40, 50 years down the road? Does that amount of nutrients that's in that area top out and can't support a fully mature tree?
I think in terms of like of root space, I think that we thought about that. In terms of the mineral soil, I don't think so. And I think to some degree, you would probably have to keep track of that as you would with like an urban tree installation. I could see a scenario where you'd have to go back and add something in or like some amendments around the tree. We haven't gotten to that point of like thinking about that, but I could see that being an issue.
And then another follow-up question on that, projecting this out into a mature tree. My understanding of how trees perform in gravel beds is that gravel beds promote very fast fibrous root systems, but those root systems are not necessarily structurally strong. So a very mature tree that has a very large canopy might not be as structurally in place if the root system there isn't there to buttress the tree or support it.
Yeah.
So is that a consideration for longer term research?
Yeah. So the new systems that we're going to build will have these like observation wells also. So they use these like clear plexiglass, basically tubes that they put in. And then you can put a camera down there and you can essentially look at where the roots are growing, like what depth they're growing at, what's the size and stuff of the root. And so those are some of the things that we'll be able to look at. And I suspect that we'll see variation based on species also for that. But yeah, I think it's a good comment.
Okay, we have a question on the other side. You seem to have our questions on the right side and the left side, so you have to hold on a little bit.
Just a quick question. Looking at this picture on the right-hand side, I was curious of that black pipe. Is that a piezometric well to see what's happening to the water table?
Yeah. So we've this system was a little bit different. We put a liner in there, and so we were kind of interested in like just seeing what the tree was doing. The liner ended up like leaking, and so it ended up being like a very like demonstration site. I think this next site we'll be able to get some more interesting data, but that is the idea is that we would have weir box to look at overflows and then have a well to be able to look at water levels inside the system.
One question here.
A quick question, really clarification. When you say 30 to 40% average interception, is that 30 or 40% average among storms, or is that 30 or 40% of total precipitation?
It would be total precipitation. Okay. Yep.
Okay, one more question here.
Are you aware of anybody, are you doing this work, looking at phytoremediation in these systems, more specifically dendroremediation, and so actual water quality improvement as the stormwater moves through these amazingly active microbial communities in the root systems? I'm particularly interested in the breakdown of hydrocarbons.
We have not, inside of these or inside of bioretention in general? No, we have not done any water quality analysis. Well, we've done like a few samples, but nothing really substantial in terms of water quality. That was kind of the next element. We were like a little bit of shoestring budget on it, and so that was I think it's a good point.
Part of the reason, so one place to look is there's some really good work being done on phytoremediation on landfills using trees. I think it's the U.S. Forest Service, and I know they've been looking at the Fresh Kills landfill on Staten Island out of New York City, and they've actually been moving materials and trees back and forth from a facility that they've got in Wisconsin. Anyway, it seems like fascinating territory, and the potential on the stormwater side in terms of pollutant load reduction seems like it might be significant.
Yeah, I know there's been some studies in Australia that have looked at like microbial action versus trees for things like nitrogen, or not trees, but plants in general. And it's a pretty high contribution from the plants, more than I would have thought, actually. Yeah.
Here's a question in the back.
A lot of the studies are with young, newly planted trees. Is there ongoing research as the trees become established and gain root systems as to how the rates of transpiration change and stuff like that?
Yeah, so I think that study, the study that we're hoping to do, I think is kind of in that ballpark. We'll be able to monitor it for a longer period of time. In terms of like laboratory stuff that we do, it's really hard to look at that, but I think it does play a huge role. I think, you know, the size of the unit that you use in a column study makes a huge difference in terms of like what you're going to get out of your performance. So that's one reason why we tried to use as big a systems as we could, but I think you're always going to run into, you know, like space restrictions. I think in general, I would say most stormwater people would say that, you know, the vast majority of things in literature in general are like new sites. And so there's been some work recently to start looking at that, but I think that's going to be a need at some point, is to figure out how systems mature like that.
Okay, we have another question from online.
What would be the typical number or spacing of trees you would recommend in a standard bioretention area? Does one tree make a large difference, or would more trees be better in a standard bioretention system?
Yeah, most standard bioretention areas are not, I don't know that they're big enough to really have the root volume for a lot of different trees. I know we were talking about some of the systems going in around here that are larger, and I think you could definitely look at that. But I think that you know, there's some general guidance of like, it's like 500 to 700 cubic feet of space for each tree. And so there's some guidance, and it's not really necessarily a spacing as much as like a root volume thing. I think that's probably a pretty good starting point as to how many trees we could put in a system like that.
Okay, we need to finish. Let's thank Dr. Jon.
Cool. Thank you.
Welcome back to the Minnesota Stormwater Seminar Series. We are moving into our panel discussion. To start this, I will introduce our panelists and ask them to give their relation to this topic. My name is Andy Erickson. I will be the moderator for the panel. To start, we're going to start on the far side with Larry Baker, who is a research professor here at the University of Minnesota. Larry, what is your relation to this topic of trees and biofiltration?
There's two. One is we recently completed a couple years ago what is probably the largest study of street sweeping in the country. And we learned for the first time, the engineers had carefully screened out all the coarse stuff when they do these street sweeping studies, which includes all the leaves and such. And that's where all the nutrients were. And when you start looking at that and you start doing it in the fall, not in the summer, as most of the studies have been done, you find that actually quite in leafy areas that quite a bit of the nutrients that come into street is coming from tree leaves. So, you know, there's certainly a relationship here. And the second, now we're doing a different study. We're looking at road salt and how it cycles through the systems. And I get very concerned about retention basins. They're little funnels for salt to go into the groundwater. I've done some quick analysis, simple steady state calculations of chloride accumulation in groundwater. And it can reach very high concentrations, higher than we'd want for drinking water, at rates that we are salting in the Twin Cities right now. One of the big questions is how much of that salt moves to pervious surfaces, either on snow piles or by diversion into infiltration basins and such. And we don't even come close to having an answer to that. But I think that we do need to start thinking about every kind of infiltration practice in terms of chloride going into groundwater.
Very good. Thanks, Larry. Our next panelist is Mike Perniel. He is a water quality specialist at the Minneapolis Park Board. Mike, what is your response or relation to this topic?
Well, I'm here, I assume, because I'm not a researcher, but the Park Board does all the surface water monitoring for the city of Minneapolis. That includes the NPDES monitoring and the BMP monitoring. So over the last almost 20 years that we have had an NPDES permit, we have a lot of experience monitoring different BMPs and how they work or don't work. And you know, I've only monitored one tree trench while we're on 50th Street, but we have a lot of other experience with bioretention monitoring, and hopefully we have things to share on the subject that will be helpful that people haven't thought of. Because also I bring the perspective of the person who is actually in the pipe.
Very good. Thanks, Mike. And we just had John's relation, about 40 minutes of that, which was great, fabulous, good information to get the dialogue started. So now again, the purpose of this panel discussion is to answer your questions. So if you have additional questions now for the panelists, not only John, but our local experts on trees, bioretention, biofiltration, we will ask them now and ask for their answers. What questions do you have?
Randy has a question.
Why do I always get that response when I raise my hand? So we've been doing tree planting for stormwater management here in the Twin Cities in a reasonably big way for maybe 10 years. I would guess, I don't know, I'm curious. I mean, I would guess we've got at least a couple thousand trees planted, and perhaps more. Could be 3, could be 4. Does that make us an interesting laboratory in terms of evaluating the performance of various systems, various species of trees? And do you think it would be worthwhile to actually go back? Because we may have more of a history here with more trees than almost any place in the country. And would it be valuable and worthwhile to actually look back and evaluate the performance of the systems we have in place here in the Twin Cities?
Well, the only thing that I would say is that I wish I had Craig Pincala here from our forestry department, because he is really knowledgeable about tree trenches and how you build them, how effective they are, some of the changing parameters. The city of Minneapolis has changed from, someone asked a question previously about cubic feet of growing medium space. The city of Minneapolis has switched from 300 cubic feet to 500 cubic feet now. And it would be good to go back because, for example, the tree trench that we monitored on 50th, it was brand new, so we saw absolutely no outflow. We saw 100% infiltration. But now, 5 years later, it would be interesting to go back and look at that. We learned a lot of other things as well because they made bump outs with permeable concrete, and Minnesota winters just tore up the permeable concrete. So they ended up having moratorium on permeable concrete for a while and just paving the bump outs. But I don't know. I didn't say this during the introduction. I probably should have. And that, in addition to leaves being, I love trees. Trees are great to have for a lot of different reasons. But there are some unexpected sort of negative externalities of, for example, as I've shared before, we have a lot of continuous reflective separators or CDS units. That the stormwater swirls, and there's a screen that is self-cleaning. And if you talk to the vac truck operators, you can learn a lot about what works and what doesn't work. And they are experiencing elm seeds getting stuck in these screens, and then they can't get them off. And for a while they're using an ice scraper to get them off. Then they're worried about damaging the screens and things like that. I just talked Tuesday to Public Works about the fact that they were vacuuming out these CDS sumps, and they're getting sand, leaves, and when the leaves break down, the vein structure of the leaves was making a mat, and so it was as if they put a straw in a chocolate cake, and because it didn't slump, and it was really difficult for them to clean this, and so there's a lot of great things to trees, but there's these unintended consequences that are affecting other, treatment devices, in totality that no one had really thought about. So, but I agree, it would be good to go back and look at those and see how they're doing.
A couple comments. One is it still astounds me, and I was part of the group that developed the first of two long-term ecological research programs, the one in Phoenix. And those two programs, Baltimore and Phoenix, have been going on for about 20 years. And there may be a new one coming up. But it still amazes me how little we know about urban nature. The urban trees, you mentioned that there are very few studies on single trees. All the through-fall studies are done in forests. Well, most 85% of us live in cities now. And we know dangerously little, I think, about urban ecosystems. And you alluded to something about coarse material, in drainages and stuff. We know more about the biogeochemistry of coarse material, leaves and stuff, in forested streams than we do in urban systems. There's virtually nothing that's been done on coarse, or very, very little, a few preliminary studies on what coarse organic material means. And you could go on, and on and on. And our studies are often, and the other problem that's been alluded to it several times is duration, sustainability of the trees and things like that. We really, really need to do longer term studies. It would be great to see, for example, a long-term watershed study where we're studying multiple things at the same place, one fairly large watershed, a couple thousand acres, studying the social interactions, all sorts of things. We have a proposal, Sarah Hobby's leading it, a preliminary proposal, but even if that doesn't get funded, and it probably won't because there's going to be 30 or 40 other proposals, that would seem to be a very, very logical thing to do. And Randy, I know you know, but I don't know if other people know, we're spending about $1.5 million now on research, stormwater research. That's probably the dominant source of research, stormwater research money now. And we're talking about spending $300 million a year for stormwater infrastructure. Well, I'm pretty sure if we took 10% of that 300 million and put it into research, it wouldn't cost 300 million anymore. It's going to cost, we could probably cut that cost in half. The other thing is we need to completely rethink our cities. well, maybe not you guys, but most of us, the grayer hair, grew up. This was we built car cities, Minneapolis, Phoenix, Los Angeles, everything east of or west of the East Coast, pretty much. And we're spread out all over the place. Well, we're coming back in. Older folks are coming back in to live. We just did that. We just bought a new house in the McAllister Groveland area. Younger people are staying in apartments and condos and such. We're moving in, we're densifying. Minneapolis is actually going the other direction now. We're going back toward densification. So we're talking about, I think, a really desperate need for green space. And that's going to have to be very multifunctional green space. So it's not going to be, a lined out detention basin built by an engineer, that has one purpose to filter something, or a pond or whatever, but it's going to be multiple use types of landscapes. And we got to fit them into very small areas. And we need to figure out how to do that really, really fast. These condos are going up all over the place. Half the time I don't know where I'm going because I'm looking for an old restaurant or something. It's not there anymore, it's a condo. Anyway, so that's a problem. And the other thing is in the urban nature, the value of the aesthetics and the other functions of urban nature, we don't appreciate well enough. It is known from studies in Chicago, Francis Kuo, that urban trees dramatically, in poor areas at least, dramatically reduce crime and improve all kinds of social behavior. Gets people outdoors, they talk to each other and all that, whereas these bare pavements don't. Now that's extreme, but I think all of us interact with nature. And we had a student a couple of years ago, Katrin Mullen, did a photographic study, sort of photographic narrative along the Mississippi corridor, and had people evaluate the different photos, how they liked them, what they thought about them. And we love photos with nature, with people in them, and the people alone or the nature alone. It's in fact, nature's a little foreboding. A forest, the edge of a forest or something like that. But when you put the people and the nature together, you love it. And of course, that's what we do in parks. But we need a lot more of that in smaller spaces. We need playgrounds and drainages and vegetable gardens and everything. If it's on the roof, it's somewhere. But we need to rethink fundamentally. Some of that is going to be management of stormwater, but that's actually a small part of the whole thing. We really need to create an urban nature, a modern urban nature. The way Cleveland, the architect, these guys built Como Park. If you've ever been to that, it's just a master stroke of the turn of the century of the integration of man and nature. But we need to rethink that a whole bunch, and not just stormwater ponds, but everything that goes into it very, very quickly, I think.
The only other thing I was going to add real briefly to not trees or the quality of life surrounding them, because I think that's pretty self-evident. It is, whether it's tree trenches or biofiltration, is a lot of times there are unintended consequences that are not considered. And for example, with infiltration, a lot of times the few rain garden projects I've been involved in, the water budget of the receiving water is not even considered. And we had a lake, Powderhorn Lake, for example, which we've had to, for the last 20 years, we've been pumping between 10 and 20 million gallons of water a year into it just to keep the water level up. And then there's rain garden projects came about in the watersheds, which are good ideas, are good tools in the toolbox. But part of the problem is a lot of times those rain gardens treat some of the cleanest water, rooftop runoff. And so you're infiltrating the cleanest stormwater, and you're not taking into account the water budget of the receiving water. And you kind of scratch your head a little bit. And then there's the other issue, which everybody knows about, which is a lot of especially curb cuts. I hate seeing curb cuts and then rain gardens, because I know what's in stormwater and it is filthy. Snowmelt is unbelievably dirty, just it's black. And it's December, January, February, March, be part of April, full of debris, brake dust, ground up leaves, etc., that just wash into these. And we need to ask, and chlorides as well, do you want these metals and do we want these chlorides in our shallow aquifers? And it's a big question, but I think it should be part of thinking the problem not just halfway through of collect and concentrate, but where does it go, what happens to it, and what's the ultimate fate. And if we do collect and concentrate, what are we going to do with it? How are we going to get it out of there? Because one of my frustrations over the last at least 10 years have been a lot of the BMPs that get put in the city of Minneapolis. And I love the fact that Minneapolis puts its money where its mouth is. They've spent a lot of time, energy, and money putting in different BMPs and treatment devices and tree trenches, et cetera. But I see a lot of these BMPs just become overwhelmed with solids, and it just kills them. And so pre-treatment's really important, one, and two, maintenance of these pre-treatments is really important, because the public works departments, I'm not throwing rocks at them at all, because they have a list this tall and they have this much resources. And we sort of need to come to grips with that somehow. I mean, everyone loves to go to a ribbon cutting for a new BMP, but the real cost is in maintaining it. And that is not lost on us. So.
I had one of those. I would just say I think if you, I bet you if you spent a summer assessing those the trees you're talking about, you'd find a lot of information on what species work and don't work to inform your manuals. Like, it's not, the assessments we did, like, they take a little bit of time, but I mean, it's pretty, like, you need 2 people in the field basically. And I think you could get some pretty interesting information on how different species survive and thrive in those environments. So I don't know, it's one of those like pretty easy studies that would give you probably a decent amount of information.
Is the size? So one of the things I mentioned was this idea that we probably have a couple thousand of these trees planted. Is that number as significant as I think it is?
That's a lot.
Nationally? Okay, thank you.
And another unintended consequence, which, you know, the PCA has infiltration standards and things like that. And I'm not saying that this was their motivating factor, but a lot of times people think if it infiltrates, it's gone. Problems it no longer exist. Well, we've been seeing shallow aquifers increase over the last number of years, and in South Minneapolis now, and I don't know what the effect of infiltration is, but we have really high groundwater levels. We also had a really wet year last year, but I would be curious to know, what are the unintended consequences of increasing infiltration causing high water tables? And I mentioned Powderhorn before, where we have pumped between 10 and 20 million gallons a year into that lake for the last 20 years. The last 2 or 3 years, we've had to pump water out of it. We pumped 0 water into it. Last year, we pumped 40 million gallons out of that lake just to keep it from flooding buildings. So.
We have a question from online.
Some of the jurisdictions in Minnesota prohibit installation of trees or shrubs in bioretention facilities. This was done because the roots were growing into and clogging the underdrains. How do advocates of woody vegetation in bioretention facilities overcome this problem?
Well, don't plant them over sewers. You know,
No, I'm not talking about
sewers. I'm
talking about underdrains in the system.
Oh. Okay, sorry. I don't know.
I'd be curious, have they documented that happening in systems?
That might be the question. Is there any documentation of this? Because I think that is a concern. You know, any kind of vegetated systems.
Yeah. So it's not a formal documentation. But a number of years ago, we had a gentleman from Sweden, Orion Stahl, who came to town, who specializes in the conflicts between tree roots and underground utilities. And one of the things that he's looked at is exactly this question of tree roots growing into pipes. And what they have found in Sweden is that trees trees love pipes. And given the option, I mean, he's got cases where the penetration into pipes is just spectacular. So it seems, how his description was that tree root systems are highly opportunistic in terms of their patterns of growth, and that open pipes are one of their favorite environments.
They like water.
Yeah.
So a question that occurred actually to me as I was thinking about the presentation and some of the answers so far is this combination of trees and bioretention specifically, right? So thinking about trees in the boulevard, we have street sweeping to capture those leaves. If we put them in our bioretention and biofilters, perhaps those leaves then get captured within that rain garden. So that's a kind of keeping those nutrients within the system possibly. I don't know if you would agree with that. And then the second piece would be, what about the shading and the interception? How does that affect the vegetation we might have in our bioretention or biofilters? So I'd like to hear what your comments, whether you have data or seen data or just what you think about that.
Well, I sound like I'm running down trees, and I really do like trees. But as Andy knows, on 37th Greenway in North Minneapolis, we were monitoring a couple of different iron-enhanced sand filters. And one of them was shaded by a large maple tree on a private person's property, and the other one was a sunny alley runoff site. And we saw some strange things happen, but about both years we were monitoring, about the first week in July, all of a sudden we started exporting more dissolved phosphorus than we saw coming in. And the one that was shaded, and it looked like when we dug down into the iron enhanced soils, it did look like they were staying wet longer. And that was the site that was exporting the most dissolved phosphorus, if I recall correctly. And so the shading is a great thing for the heat island effect, but for some BMPs, the shading looks like it's impeding them drying out and functioning like they're supposed to. Sort of an unintended consequence.
And just generally, we've had this paradigm from the 1970s that BMPs trap pollutants. They remove pollutants. Well, they with some exception, there is some actual BOD removal that goes to CO2, but that's not the major pollutant in urban systems. You are trapping things, but as you alluded to, where do they go? And we need to think very much. We've advocated for this in the first stormwater manual. We wrote that chapter 2 on stormwater processes or BMP processes. What actually is happening from a biogeochemical standpoint? Is nitrogen getting denitrified and going into the air? Is phosphorus being absorbed on soils, and therefore now you have contaminated soils if you have to dig it up, or at least you've got to do something with it. Ponds, you need to you're just trapping stuff in there, and it needs to be removed. Or are you actually degrading pollutants or otherwise getting rid of them? With chloride, for example, we don't think there are processes that remove chloride in the natural environment, at least not permanently. And so you have to go to source reduction. And a lot of this kind of thinking about process would lead you toward source reduction, trying to stop the pollution in the first place, not trying to treat it afterward. So it's really kind of primitive thinking in a way. On the other hand, in very controlled systems, in wastewater treatment systems, engineers understand very well what's going on. They know exactly what's going on with denitrification and BOD reduction and things like that. It's a carefully honed process, and it works extremely well. But you don't have that kind of operational control in stormwater ponds and such. And it's been, again, this second step that we really didn't even consider when we passed the Clean Water Act in 1972. We added the amendments in 87. There was really no research program to support it, or at least there was a bit, but not nearly what needed to be done. And so now we're left with trying to figure out, well, do tree leaves, what happens to tree leaves and the drainage at the bottom and everything else. We're way far behind, I think, considering the degree of regulation. And I'm not suggesting we reduce regulation. I'm suggesting we increase the research rather dramatically, like tenfold.
Yeah, the only thing I would add is that I've seen a lot of people identify problems and then identify solutions to collect and concentrate, but not necessarily think it through about what happens to that. And you know, this isn't a biofiltration, but we have a large underground sand filter, Lowry and Marshall, that didn't have enough pre-treatment, and the organic material, the leaves and things, have completely plugged up this huge underground sand filter. And it's only 5 years old, and they tried cleaning it, the top of the organic material off, which again, an unintended consequence is when you get a lot of wet organic material in an underground chamber, you have no oxygen down there, and so it's difficult for people to work down there. But Public Works is amazing, and they've got it ventilated and got enough, got people down there, and they've vacuumed the surface of it out, but the pore spaces is plugged. And so now everybody's scratching their heads saying, what are we going to do with this? And I wish that it would have been designed with, okay, we're going to collect and concentrate, but then what's going to happen to this material? Design the ability to back flush the sand filter so that the pore space can be opened back up. But you know, those questions haven't been asked until recently, until now, when we have a lot of these BMPs that are having problems of being overwhelmed with solids. And
if we knew about the biogeochemistry of coarse solids, we would not have this problem, or at least we'd know how to deal with it.
What other questions do you have for our panelists?
So for Minnesota, we're seeing kind of a shift of species that are potentially could do better further up north, and we're seeing some changes in climate conditions with rainfall and flooding, and that impact on species selection. I'm curious if more further south in Tennessee, if that's something that is also of consideration when you're choosing your species for the different systems.
I don't think that I've heard much about changing species selections. But I do think it's an important factor. I think you know, people like farmers, et cetera, are probably thinking about that a little bit more than we are. I mean, their livelihood depends on, you know, what they're growing, and so I do think we probably need to think about, you know, what species selection. We've also talked about just like genetic diversity of species in the urban environment. So I suspect if you went into the city and looked at like a particular species, you know, if they're frequently bought from the same vendor, they probably have the same genetics. And so if you did have like a you know, like an insect that came in, it could probably take them all out. So I think there's a few things like that we haven't given much thought to.
Just for John's benefit, I think probably most of you guys know this, but we've had emerald ash borer here, and they decided that ash trees were a good thing they grow fast. They're decent boulevard trees, but now one by one, I mean, not one by one, hundreds by hundreds, they're getting cut down. So we're removing our ash trees. That was a mistake probably to plant the same species.
Yeah, we actually talked about that a little bit in our June seminar from last year, and we kind of identified that as a great opportunity, right? To rethink, what do we do with our boulevard trees? What species do we choose? How do we go about this maybe better or more forward thinking, right? What other questions do you have for our panelists? I know I have another question. I wanted to ask about maintenance. So thinking about trees and maintenance, we talked about that a little bit previously with seeds, right, and leaves, and how that can affect our infrastructure, and how do we capture that, and then how do we have to maintain that. What other lessons can we learn from using trees, bioretention, biofilters, and these heavily vegetated systems when we think about maintenance, proper maintenance and maintenance cycles?
I think one of the comments is just on the lines of clogging of pipes and stuff like that, is to try to learn from the that forestry community about tree physiology and about how trees function, and are there specific species that would be more prone or less prone to have some of those issues. So I think we could learn a little bit from other disciplines in terms of what they suggest. I think it's easy to like assume that they understand or that they are like aware of the stormwater field. I know that's kind of what I did. It was like, I just kind of assumed my collaborators had already knew about stormwater and how the systems worked and stuff like that. It's not the case. They don't necessarily know what's going on in our field any more than I know what's going on in their field. And so I think the more that we can collaborate with a diverse group of people, the more we find those like interesting solutions. So I think that's a big thing, is looking to other disciplines, and as many of the problems that we can work out beforehand, obviously, the better.
One thing that we've thought about and looked at, we haven't really delved into it, which is stormwater is not stormwater. It's not stormwater. Different watersheds seem to produce different types of stormwater. And a simple example is, with the iron enhanced sand filter, everybody points to the Beam Avenue site over in Maplewood. Well, if you look around there, there's no trees, and it treats just parking lot runoff. Well, I can tell you, parking lot runoff doesn't have a lot of organic material in it. It's not, it might have a little bit of sand from the sand salt, but it's not going to be a heavily used roadway. And it's going to look really different than a downtown street or a densely populated part of the city. And we've thought about looking at, and I don't know if anybody has looked at, what BMPs work best in what different watersheds that have different, not only land uses, but different tree types. And because it's, tickling out some of the nuances, but there's a lot of different things in different types of land use watersheds, and not all BMPs work for everything.
I've actually forgotten what the original question is, but I'll riff off the other some of the responses. And following this, one of the things that we've not done is we've had a stormwater program now for 15 years in the state. We have not gone back and looked at how successful we are. The stormwater folks tend to look only at individual BMPs and such, and not at the whole system. And in particular, nobody wants to go back and say, well, this worked or this didn't work. There is some trend analysis that says phosphorus levels are down a bit in urban streams, but we don't know why. And you could say, well, who cares? I'm a politician. We did it. Who cares why? Well, it's entirely possible. For example, it might have been, hypothetically, the lawn phosphorus ban that we did in 2003. And that we would know, several of us who kind of understand lawns a bit would say, yes, it would take several decades for that to happen. So if it's happening now, that's right on schedule. If that's a case, other people might say, well, no, it's we put in all these BMPs and that's what did it. And it's really important to know which, because if it was a phosphorus ban, that was really, really cheap. It didn't cost much of anything, really. If you're building hundreds of millions of dollars worth of BMPs, that's really expensive. And we could go through, I'm pretty sure we could go through now and do a retrospective, a 15-year, 20-year retrospective, and look at what was happening in that landscape. And very likely, and this is based on my work with other kinds of environmental problems, it's not one thing. You can't say, well, it's BMPs, it was this, it was this. Probably a good part of the change was due to things that are not related to water management at all. We converted from agriculture to residential, and typically that would have somewhat less erosion and phosphorus. In areas where we've built out during that period, we probably had more construction erosion, and you'd probably see signs of that at various points, when it happened, where it happened, and all of that. If it's anyway, you use various kinds of biogeochemical fingerprinting, flow analysis, and other things to try to figure out what happened and learn some really valuable lessons about what caused a decline in phosphorus, or what causes an increase in chloride, and really use that as a guide for the future. You know, what didn't change, or what changed incidentally just because of land cover practices, you know, what people built. It had nothing to do with their stormwater program at all. But we haven't done that analysis, and so we continue to overspend on what I think is very narrowly targeted stormwater BMPs and such, at the expense of trying to figure out what is really happening at the urban watershed level. And that analysis is way overdue, I think.
I'm on this side.
Dr. Hathaway, you hit on one of my favorite topics, which is collaboration between disciplines. If you could elaborate a little bit on that, what can stormwater people learn from urban foresters, landscape architects, vice versa, and how do we move forward in improving the communication between those?
I mean, it's going to sound like pandering. I think what I've learned, so I first started working at UT, and I started working with another professor in geography and one in social work. And what you learn from like off the bat is like you communicate very differently. You collect different data, and it takes a while to understand somebody's methodologies and approaches and how they look at problems. And so I think it's hard to do like drop-in collaboration where you just kind of like, yeah, like I'm going to collaborate with this person for, you know, a couple weeks. Like you never really understand what they do. You know, one of the things I did early on was just like, could you share some of your papers with me so I can read them and like understand your methods and like how you go about doing things. After the fact, I learned that she thought I was trying to like vet her like abilities by asking for papers. But I think it's important to understand how different people work and how their methodologies, you know, work. And so I think it takes a little bit of work on our end. It takes a little bit of work on everybody's end to understand how those relationships work. But, you know, in the case of working with forestry or any other discipline, you know, it's interesting how many of the things that we scratch our heads about, they have a pretty reasonable solution for. They just don't know the problem, you know, and so that's, I think disciplines they don't know each other's problems. And I think that's probably where the shortcomings come in, is a lot of times there are solutions, but we don't communicate enough to know, you know, what the other group is dealing with.
Okay. Yeah, I'll comment on that. I've probably written papers with at least 50 or 60 people, faculty level people, not including graduate students, and in everything from chemistry to political science and economics and other things. It does take a long time. I'd say it takes several years to really understand how other disciplines work. Early in my career, and then just during that era, okay, so like say the 80s and 90s, we did a lot of parallel play. You know, we sort of did studies on the same site or such, but we were really doing them differently. You know, and we'd communicate twice a year or something like that, but not really working between disciplines. And the ideal is where we can do studies that one writer calls interpenetrating epistemologies, where the hypothesis that you're trying to test, or the idea that you're trying to test, is not one from engineering and it's not one from social science. It's one that is truly interpenetrating. The social scientist couldn't solve the problem and the engineer couldn't solve the problem, but together, by thinking through, you know, you can solve the problem. The other is, Mike, I'd say not just disciplines, but also sectors. We're doing a study on de-icing now. It was sort of a first step type study. And one of the things we want to do was communicate with the road crews and such. And there's been a tendency in science to recommend, we're telling you to do this or telling you to do this. I've never driven a snowplow. I have no idea how to do it. I can tell you where the chloride is coming out, when it's coming out, what storm that was related to, and we can get computerized data from your truck that say how much salt got applied. But I have no idea what to do. You have to decide that. And in one workshop we had in the first year of the study, we found this one huge peak that was about 80% of the salt for the season. And we showed that to them in a room about like this. And they just went nuts. They were trying to figure out what they could be doing differently. They took it very personally, but in a good way. They decided their bosses should buy some new snowplow blades that cut the ice better so they wouldn't have to put so much salt down. And they did. I mean, they practically told their supervisors, not ask or suggested, buy these new blades. We can do this. And they bought 5 of them. And so far they seem to be really helping. So here's a case where, we can, as scientists, we can collect science and hopefully we can present it in a way that can be comprehended, which means very little graphics and such. But a lot of times it's the audience, it's the receivers who are going to be making decisions about this stuff. And they're in a much better position to do that than we would ever conceivably be. So.
So I have a similar communications question, and it's going to start in particular to Dr. Hathaway, if I may. There appears to be a bunch of really interesting new stormwater tree research work being done in places where it wasn't being done, when I was looking at it 5 to 8 years ago. That's terrific. But it means that we're generating these new research results. And my question is, what's the status of the, for lack of a better term, technology transfer process?
Yeah.
So where the new research results are actually translated and communicated and become actionable information for folks at the local implementation level. Where does it stand now, and how do you think it can and should be improved?
I'm going to count this as part of my Forest Service on my reports to them. The person that I work with the Forest Service at Athens is one of the things he does is technology transfer, and so we've been working with him on some various handouts and stuff like that, and technical notes that we can provide to the forestry community. We tried to do a few different webinars and kind of like free access stuff that we've put out. But yeah, it's hard to hit. It's hard to figure out how to hit all the communities and interested people. I think we've tried to do a couple different avenues, through conferences and papers, maybe more for academics, and then we've tried to do some webinars and some more like tech notes and stuff for general practitioners. But yeah, it's difficult to figure out how to hit everybody at the same time. But that's kind of been our strategy, is to try to hit it at different levels. My wife is an engineer. She worked for the city of Raleigh for probably 10 years. And I was talking to her one time and I was like, oh yeah, we're going to write this paper. And she was just like, John, nobody reads your papers. Nobody reads papers. So it's like, okay. So, you have to reach other people in different ways.
We had a similar experience almost. Who was the head of the Ramsey Washington Cliff Eichinger? I was talking to him about that, and he said exactly the same thing. He says, Larry, no one reads your paper. He wasn't referring just mine, but just generally. People in the practice community don't read academic articles. That's when I started writing a couple for Stormwater Magazine and getting out there giving more talks and stuff. And they also want tools more than anything else. I haven't actually done this, but it was suggested, and we were on a panel with urban researchers and city folks like you. And they said, we want policy briefs. We don't want 20-page reports or 100-page reports. We don't have time to read them. And we want short, snappy pieces. And I think academics have to learn to do that. Unfortunately, the reward system is virtually 100% peer-reviewed papers. You're, I think, actually slapped on the wrist for doing anything other than that, which is unfortunate.
Yeah, at the park board, what we do is when, as part of the NPDES permit, we write our annual report on all the state of all the lakes and the beaches and also the stormwater and BMP monitoring that we do. And we hope that, we always struggle with what kind of an audience to write this for. And because it can be really technical, but we don't want to make it all acronyms and word salad either. And it's a challenge to try to get this information out. But we hope that our annual report, which is incorporated into the city's NPDES report, does get read by people and does make a difference.
Yeah, just a footnote, Rand. If you look at how many people get a peer-reviewed journal, typically 3,000, something like that. Now, how many people read Stormwater Magazine? That's about 30,000. How many people read the Star and Tribune? That's 300,000. Right. You could have your lifetime of readership of your journal articles in one editorial in the Star and Tribune.
So we have another question from online.
Yes, a follow-up to the emerald ash borer discussion from earlier. Many cities are in the process of removing diseased trees and deciding what to replace them with. What would you consider to be the primary variables when selecting urban street trees?
You're looking at me. We've seen this has actually been interesting in various parts of cities also. I know East Knoxville and had issues where old growth trees die off and then they just don't get replaced. And it's kind of an issue that we've had. Our urban forester in our city has been trying to remedy and put things back in. I think that, like we talked about, I think that thinking about what the climate is going to look like over that tree's life is important. I think replanting in a way where you give a tree more soil volume is important. And being conscientious of things like utilities and sidewalks, and I think you're less likely to have issues like that with a tree if you give it enough soil volume to be able to kind of spread out a little bit. The other thing is I think localized people in the local forestry community often have better ideas about what's going to work than taking something from another region. And this is like the trend in stormwater is we've realized this in Tennessee that a lot of the stormwater regulations and approaches have been developed in the mid-Atlantic in the US, and then it just kind of like everyone copies everyone else's stormwater manual and you end up with things that aren't necessarily catered to your specific environment. So I think those are what I would suggest is the better localized information. I think it's better for selections.
I would add to that. I was getting ready to say, yeah, we have a couple good urban foresters on campus, or urban tree people. Specifically tree people. I'm an engineer who dabbles with trees. But really, it's one of these things that's very interdisciplinary. It should involve a lot of different kinds of people. And I want to give an example. Back in the mid-1900s, when we were starting to build, we had invented toilets, but people were starting to use them. They're getting more volume. You couldn't use your cesspool in the back anymore, or your latrine. You were putting this stuff into the storm drains, which is what we call now combined sewers. And at the time, as cities started doing this one by one, there was a intellectual fight, debate, whatever, between the engineers and the public health people. The public health people said, don't combine the sewers. This is stuff can communicate, this transmits disease. It should be treated over here as well as we can, which of course wasn't all that well back then. And the engineers said, no, it's quicker and cheaper to put them together, and then it can go downstream. Their natural treatment process, again, didn't really understand that terribly well, and it spread typhoid downstream. Cities like St. Louis and others we had a wave of epidemics of typhoid. So we could have the urban foresters say, yes, here's the right kind of tree, and I'm thinking, I've heard this from in the immigrant communities. Sometimes they like fruit trees. Well, that's not what the urban forester might have thought, the traditionally trained urban forester might have thought of, but maybe it's a good idea, fruit trees. You go to Mexico, people have fruit trees everywhere, and in their lawns and stuff. It's something that needs to be done in consultation with the community. It does need experts. It needs the people who manage the trees, because there's a lot of cutting and stuff going on. But we really need to think about that in a kind of a community way. And I don't know that we're doing that. I haven't heard that is happening.
I do know a little bit in Minneapolis. We are starting to get a lot of requests from citizens to do it's like urban gardening or plant more fruit trees and things. And forestry sort of struggled with how to answer that. And but then if nobody picks up the fruit, what do you do with the fruit and things like that? So it's a question that is coming, and to the online person as well. We were talking this morning before I came here about the fact that I totally agree. A lot of the stormwater treatment practices were started on the East Coast, and then we've sort of just copied them. And it's almost, we do have BMPs for cold weather climates, but it's almost like we need a continental climate focus group or area, because we have such extreme temperatures where we can go from 50 below to 95 degrees. And how do you have plants live in that climate, let alone we have, if you want to get really depressed, we have winter almost half the year. And how do we make things work with plants with those parameters?
So with that, in the interest of time, I would like to start our closing. What I'd like to do is give each of our panelists this question. So what is maybe one key takeaway that you would like our audience, both here in person and online and future when they're watching the recordings, to take away from this discussion and this topic and presentation on trees and biofilters? We'll start down with Larry on the end, and we'll finish with our keynote speaker.
Yeah, I'd like to reiterate the point about densification and the need to have very functional green infrastructure that is both room for human experience of nature in urban environments. We're going to need that a great deal. Stormwater functionality is part of that. Multiple uses of water is part of that. Ponds and drainage and trees and wetlands and all that. I think we need to do that sooner than later, especially in Minneapolis, because we are growing and we are densifying.
The thing is, okay, if there's one thing I want to drive home, it's pre-treatment, solids. Pre-treatment's really important. And the second part is it's really important to maintain those pre-treatment devices and remove those solids. And lack of maintenance is a problem, just not just for BMPs, but even like biofiltration. I can't tell you how many I've seen where once cattails get started, they just take over the whole thing, and then you're back to almost total reconstruction in terms of plantings and things. The other little things is like whether it's a tree trench or other BMPs, when you're designing a BMP to collect and concentrate materials, pollutants, have a way to remove them so that they're permanently disposed of or handled with, and design the BMPs so that they can be cleaned or flushed, so that it's not total reconstruction when their lifespan or the pore space is full. And then the other little things is when you're constructing these BMPs, I don't care if it's a tree trench or not, have somebody visit the site every day. It's really important. I've seen a lot of things constructed at the park board where people rely on reports from the contractors rather than actually visit the site. And then subsample test materials. If they call for washed rock, subsample that material. We've had one where apparently the contractor, it's cheaper to get unwashed rock. So if they put unwashed rock in there, all the fines plug everything up, and then it's just a mess when it's done. So make sure you're diligent about durable about subsampling the materials to make sure it's right. And then the last thing is kind of crazy. When you're done with the project, have all the contracts written so that you have as-builts. A lot of these BMPs that get built, whether tree trenches or whatever, there's blueprints, and then it's how it actually gets built. And then you show up a few years later and we're supposed to monitor it, we're supposed to fix something, and you have no idea what it actually looks like underground because as-builts were not done. So that's important. And then I suppose lastly, just kind of leave you with this crazy idea. And that is obviously, since, throw it away, there is no way, everything goes somewhere. Ask yourself we're trying to collect and contain phosphorus, for example, and we put it in these different BMPs and try to contain it and take it away. But tree trenches and biofiltration transform that phosphorus into something else, plant material. Rather than phosphorus be a negative externality, how can we make it a positive externality? How can we transform it into something that we do want, whether it's flowers or trees or some fiber material that's valuable? And that's it.
Mine just collaboration. I think we have a lot to learn from different disciplines, and specifically trees. Just people who understand tree physiology, how trees function, and the types of environments that they like to live in. And I think some of those questions about like what tree works best in what environment is probably not the best question for an engineer to answer. So.
Very good. Thank you. What I'd like to do now is I'd like to thank our audience, both in person and online. Thank you for joining us today. Please help me in thanking our panelists and our speaker.